So we would like to evaluate this surface integral of f over the surface S, or the flux of f, where the function is given by this expression and the surface is a paraboloid that lies above the square, this square, and has an upwards orientation. So here is a mu pad graph, and what we have is that you can see this red surface is part of the paraboloid that lies above this square. And what we mean by the upward orientation is this, that if we write this this surface, or express this surface by or through this function, say gxy, I mean, we create an expression here and then look at the surface as a graph of gxy equals 0, rather zxyz equals 0, then the normal vector, or this unit normal vector that you have here, okay, then this vector should be along what? Along the gradient of g. So what we had is this, that in our lesson, that if the projection of this surface S in the xy plane is, say, R, for example, here, R is this region, or this square region in the xy plane. So with the upward orientation of S, this surface integral will be, this will be, again, R is the projection in the xy plane here, so that will be f, then dot product with the gradient of g, okay, dA, where now we are in the xy plane. So what we would do first is that we would compute the gradient of g. Let's do that quickly. And so now we are computing the gradient of g. Now notice this, I have made a mistake here. That is, when I took it over to the other side to form g equals 0, these would change signs. So I made an algebra mistake. I'm sorry about that. So if we compute the gradient of g here, what that will be, that will simply be the partials with respect to x, with respect to y, and that with respect to g as our three components. And then let's compute our f dot gradient of g. And notice this, when we write our vector f here, now what we have is we have x, y, and for z, what we have is z is given by this expression on the surface S. So we will change z to this. Okay, remember the procedure that we had in the lesson. Okay, so we got this, and in the third component also what we have is z is this right here, and then we have x, and then we got dot product with gradient of g. Okay, just routine calculation. All right, and then f gradient dot gradient g would be, that would be a scalar. So you have 2x square y, and then we have 2y square z as a function of x and y here. Okay, and then plus 1 times this or 1 times this third component. So let's just write it as it is. All right, so this is what we get for gradient f dot gradient of g. And then when we go to evaluate this, then what this would be is that this is going to be the integral of this quantity, or double integral of this quantity. This is square region in which x varies from 0 to 1 and y also varies from 0 to 1. So our integration is going to be integral from 0 to 1. Okay, and so both the limits for limits for x and y both are going to be 0 to 1. So here it's just the same symbol again. Okay, and then we have this thing here, this expression here. All right, and doesn't really matter what is our order of integration in this particular case. So if we compute this with the typical process of iterative integrals, the value of the surface integral is going to be 713 over 180. All right.